All right, so the sets of lectures here are going to introduce us to some of the concepts we'll see in our discussion of a new quantity that we're going to call momentum. So momentum, for the lack of a better word, is the oomph by which different objects with mass and velocity interact with each other. So simply speaking, the momentum is based on how much mass an object has and how fast it's traveling. Now, these are vector quantities because while mass is a scalar, it doesn't depend on direction. Velocity is a vector. Direction matters. So that means momentum also is a vector. The direction you're traveling at is going to matter with how you interact with something. If something flies at something this way, that's going to affect how it interacts. If it's flying this way, it's going to affect how it interacts. So this quantity here, based on how fast you're going, how much mass you have, will help determine the outcome of some interaction. Where momentum becomes useful is, like with energy, momentum is another one of our conserved quantities. That is to say, if we take all the particles that are going to interact and we look at some before time and we count up all the momentum, which is simply a matter for us going, what is their velocity and what is the mass of every particle that's about to interact. And in the before time, we sum up all those momentum. In this case, this formula here just assumes that, well, there's two little masses and they each have some velocities. That's why we have an initial momentum for particle 1 and an initial momentum for particle 2. And then something happens. And this something can cover a wide range of things. Maybe two objects come together and they stick together and they move off in some direction. Maybe two objects collide and then they break apart. They break apart here still as two pieces, but they go off in weird directions. Maybe these are two things sitting together, like pieces of material inside of a bomb, and then some explosion happens, and later the material is moving away. All of those different situations are still going to satisfy the idea of conservation of momentum. We sum up the mass and velocity of all the initial pieces. We sum up the mass and velocity of all the final pieces, and we'll know how those pieces will be behaving in terms of what their final velocities will be. As a side note, going back to the bomb example, we might be starting with two pieces, but after the bomb, maybe it breaks up into multiple pieces. So for every piece we start with, every amount of mass and its initial velocity in the before, we go to the after case, we look at all the mass, we count up mass and the velocities, and we still track it. Total initial momentum should equal the total final momentum. Here's just this expression rewritten where we're just saying, okay, well, we know that the expression for momentum is just mass times velocity. So here you could see that, hey, we have some expression that if I knew a bunch of masses and I knew, say, some initial velocities, and I observed that this particle after the interaction is going off with some velocity, we have the math available to solve for this unknown velocity here. Another quantity that's useful when talking about momentum that helps us tie back to other quantities that we measured, namely the quantity of force, is the idea of the impulse. So the impulse, by definition, is just how much has the momentum of an object changed. So the change in momentum is the impulse given by this quantity J. And this change symbol here just means, final momentum minus initial momentum. Now, of course, because momentum is based on the velocity, and the velocity can be tied to the expression for the acceleration through calculus, that means that this change in momentum expression here can ultimately be written in terms of the integral of the force that is applied on something over the amount of time that goes by. So now we have just like how we have several other relationships connecting our kinematic expressions and forces and energy. Now we have a relationship that would allow us to go directly from, we applied a force for a certain amount of time and the momentum of an object changed. And see, so this is why this expression makes sense, because it makes sense to us sort of intuitively that if I have some object and I exert a force on it, then if I exert that force for, say, a small amount of time, then the momentum, that is how fast it's, this mass is initially moving compared to how it's later moving, that change might be small. But if I exert that force for a longer period of time, then I have a chance to speed the thing up more. So this change in momentum is going to be bigger, thus the impulse itself is bigger. Finally, this formula here, if we rearrange it, we integrate the force to get this change in momentum, that means we can unpack this. The opposite of doing integration is a differentiation. So we get another nice expression that allows us to have an idea of, well, approximately what size force would we have to apply if we wanted to cause an object to change its momentum by a certain amount. And it turns out in this case, the other piece of information that we have to know is how much time goes by. So if we observe that an object changes its momentum by this amount in a certain amount of time, we have an idea of how much force had to be applied in order to make sure that change in momentum happened. This kind of expression can be very useful when we're looking at scenarios like, let's say we're wanting to analyze a crash, and there's a car that was initially moving, right? So it had a certain amount of mass and it had a certain amount of velocity, and then that car hits a barrier and it's come to a stop. It still has the same mass as before, but now its velocity is 0. So its momentum changed by a certain amount, so we know how much the momentum changed. The collision may have happened in a certain amount of time, right? So we can either externally watch the collision and just see how quickly it took for that car to be going from moving to not moving. And then from there we can calculate, well, how much force is experienced by the car, and by extension, by the passengers within the car. We'll be coming back to you later using this formula for understanding why certain things are designed. For example, why is it that cars have crumple zones? Well, intuitively we can look at this formula and say, hey, when a car is built so that it cannot crumple at all, that means when it moves along and gets into a crash, it goes from moving to not moving in a very short amount of time. And so if this, for a fixed value, if I make this delta t value very small, that means that car has to experience a lot of force in order to be brought to a stop. Say I take the same car, and now I make it so the two ends can crumple a bit. That is, when you go and you hit something, the car is actually, the pieces on it can be deformed and stretched and whatever as a part of that collision. Well, that means as the car goes along, it's still going from moving to not moving. So this piece hasn't changed, but the actual time it takes the car to come to a stop is going to be longer, because now the car has to come in and the parts of it are deforming. Of course, the crash still happens very fast compared to our perception, but it still makes it take a longer time for that car to actually be brought to a stop. So now, because this quantity is bigger than it was before, that means the size of the force had to have gone down. So we can use expressions like this to sort of reverse engineer or break apart why it is certain mechanical systems behave the way they do. So again, we introduce a new quantity called the momentum. It's another vector we have to deal with. Momentum is another example of a quantity that is conserved. So we sum up all the initial momentums. That will equal all the final momentums of all the pieces, which allows us to have predictive abilities. We know how two things were interacting before. We have a way of trying to determine how they will interact after. And then finally, through this quantity called the impulse, we have another connection between, in this case, the quantities of how much force is applied, how long is a force applied, how much does the momentum of something change, or how much does the momentum change. All right? So in some of the next lectures in the lab piece, we'll make use of some of these formulas to calculate some different systems.